Welcome to the part 3 of week 2 lecture. This one is probably going to be the most relevant to your project design, so please pay more attention to this one. The motor drive selection including 3 steps. First is to understand the parameters that determine the choice of your motor, such as power, speed, or torque requirement. The second step is to do the calculation, actually being able to convert the information from the workload side and calculate it back to the information from the motor side. So the motor to drive load synthesis. And the last step is to consider other issues like environmental issues, dust, moisture, and those other related issues for the selection of the motor. Motor selection criteria. The following list are the major criteria you need to consider when you select a motor to drive a system. First is what electrical supply do you have? What's your voltage and your frequency of power supply? And is that a 3-phase or single phase? What is the load power and the speed requirement? So in your case, in your project, this load power and speed is given. In some other case, you have to calculate based on the task you're going to do. And the next step is using the load power and speed, you calculate back towards the motor. What's the motor power and the speed? And what's the characteristic of motor power, torque, and speed curve? And then we consider the special starting or running up conditions to make sure the starting up property can be satisfied. The last one is the operation environment. Is the environment very moist or dusty, very cold, or in the inside a clean area, or is outside in the desert? So all those issues need to be considered. First thing to consider is what kind of power supply is available for us. Do we have DC or single phase AC or 3-phase AC? And for different power source, what's the voltage level and what is the frequency available? So in Australia, we have 220 volts, single phase, and 415 volts, 3-phase with 50 hertz. Third thing is for any power supply, there's a certain limited current you can draw from the cable. For example, the household power supply in Australia is limited to 10 amps for the normal wires and 15 amps for the special kind of oven and other equipments. In Australia, typically all the industry related workshops will have a 3-phase 415 volt power supply. So that's a good thing. In USA, many of places you're going to have a single phase 110. If you want a 3-phase, you have to get a special kind of way to get that. So that's a good way. In Australia, we're trying to focus our design in 3-phase AC induction motor because that's kind of the most usable for this kind of conveyor, kind of continuous motion design. Power requirements are the most important calculation we need to do for the selection of a certain motor to drive a certain load. For our conveyor, we can consider it's a constant load, means the load doesn't change from the static motor condition to the normal running or full load condition. The torque and the load speed normally is on the output side. We have to convert all those values to the motor side. We have to know what the motor sees, the speed, the torque, and the power. So while we're doing that, we have to allow the efficiency of this mechanical gearbox. Each level of gears will have some energy loss, so the efficiency factor needs to be considered. When the load is actually not constant, then sometimes we have to consider this duty cycle. If say for 50% of times running 100% load, then there's another 50% time we're running only at 70% load, then we use IMS value to do the average to get the average payload or the equivalent payload. So typically motor are selected to run continuously around 70%, 80% full load. We don't want to design the motor only running 50%, or we don't want to design a motor that running over 100%. So certain kind of level of payload will make the motor running in its best efficiency. One more thing we have to make sure is the run up times. So this is the startup times for the motor. We want to make sure this time is not too long, so the motor doesn't run in very high current for extended time, so the motor doesn't get burned down. And actual running speed needs to be checked, because the motor can only run at certain level of speed. We consider only the direct online mode. The motor is connected to the line frequency 50 Hertz. You don't have a variable speed drive. So in that situation, you can't really kind of decide the motor speed. The motor speed only providing a certain values. So you have to adjust your gears to kind of get to the exact speed you want. Maybe a little bit more and a little bit less. Power requirement when we have our load is changing regularly. So we use duty cycle in this case. For example, in the figure, you have a P1, a small power consumption for a certain period of time. Then this goes to a higher power consumption P2 for a shorter period. Then go back to P3. Then P4 with maximum power. Then go to P5. Then you go back to P1. So it's kind of a cycle through these different power stage. We have to somehow get an average value of power consumption for the total load. So we call this root mean square average of the power. So from power point of view, we can't simply just add them and divide by how many the total time. We have to do this kind of square root average. So the formula to calculate is that the RMS power, the root mean square power, is equal to the square root of P1 square T1 plus P2 square T2 and so on, divided by total time. So it's kind of the time multiplied with the power square for each part, then do the square root. This is how we calculate the average of the power. This actually physically makes some sense. If you just average P1 to P5, it doesn't really make any sense. Be careful that for different motor supplier, if you look at their catalog or their introduction menu, it will have certain way of kind of how much duty cycle it can sustain. For your project in MECH215, we consider the load is a constant load. So this you don't have to calculate this part. Torque speed requirement where motor is running at the nominal setting. So this is when the motor running at the desired speed. One thing to be careful is, we mentioned that a few times, we can't really select a motor as whatever speed we want. The motors are designed based on those nominal speed. So for example, if you have 2 poles, your speed in Australia will be 2880. You have 4 poles, you get 1440. You have 6 poles, you get 960. You can't really get a motor to run at, say, 2000 RPM. It doesn't really exist, because if you don't have advanced control, you connect the motor to the power line, the motor speed is decided by the frequency of the power supply. Most loads, however, is running in low speed. Like you can't have a conveyor running super fast. Normally those industrial environment things are moving much slower than the motor speed. That's why we have to design gearbox at the first place to actually reduce the speed. And the ratio of the motor speed to the output speed is called a velocity ratio. It's called NV. So it's the speed difference between the motor and load. And this ratio NV is also create another factor that it multiplies the torque that motor can sustain. So if the speed is slowed down by mv times, the torque actually goes larger by mv times. So we can do this calculation in the formula. The load torque from the motor side is equal to the torque, actual torque from the load side, divided by the velocity ratio, and also consider the mechanical efficiency here. So with the formula we see TLM, so that's the torque of the load seen by the motor. So there's a slash m, which means that's what the motor see, is equal to TL, is the actual load, divided by mv, which is the velocity ratio, or we call it gear ratio, and then multiply with the efficiency. The efficiency depends on your gearbox design, like different type of gear engagement will have different efficiency. And because the efficiency is always going to be less than 100%, so you always have to consider that factor. When you design your motor, needs to be a little bit more stronger or harder than the load power. After we select a motor for our design requirement with certain RPM and power, we have to consider the starting requirement. Here are two factors to be considered. First is the torque throughout the startup process needs to be always larger than the load torque. Otherwise, the machine will not be accelerating. You will not get to the nominal speed. Secondly, the time during that startup should be short enough, or the current going through that startup needs to be small enough. Otherwise, you might end up to have a very large current going through your motor for an extended period of time, and then motor will be damaged, or your system power supply might be damaged. Your other components on the power supply might have been impacted. Now let's look at our famous motor load torque speed curve. Let's ignore this red curve. Red curve is when the load is actually changing during the startup. In our case, we look at the green line, which is the constant payload, and also the blue line, which is the torque generated from the motor from static to its nominal or rated RPM. So the intersection point between the blue line and the green line is the input torque, the motor torque, equal to the load torque. When these two equal, the motor is not going to speed up or slow down, will be kind of stable running at that speed, and that's what we call it rated speed. And you can see the lowest blue point, I've drawn an arrow over there, is kind of the minimum torque available for acceleration. So at that point, let's say it's 250% of the rated torque. Then because the load will have 100%, so we still have 150% left to speed up. So the overall torque in this case is sufficient for the motor to start up, but we still have to check how long it will take goes from 0 speed to this rated speed. What if in that condition it will take too long for motor to stop and then it will generate too much heat? What can we do in this case? We can actually increase the MV, the gear ratio, from say 1 to 2. In that case, we just double the gear ratio. Our speed will be slower, so we have to choose a higher speed motor. But in that case also, the load curve will be only 50% compared to 100% in the previous case. So get an extra 50% of the torque to be able to use to start up. The motor will balance at a different work point. there are two different ways to kind of measure the starting requirement. One is from the inertia. The other one is by measuring the time. From Newton's law, this is Newton's law for rotational movement. T is a torque equal to J, inertia, multiplied with d omega dt. That's how fast the speed is changing, rotational speed is changing. So that's rotational acceleration. So from this equation, we know that if the torque is a constant, available torque, then the larger the inertia, it will take longer for the system to start from zero speed to the desired speed. So equivalently, you can limit the J or limit the T to limit our starting situation. So J is the moment of inertia. In some other system, we use I to represent moment of inertia. Sometimes people use G to represent moment of inertia, just different way of using symbols. In our case, the J is a total moment of inertia that seen by the motor. Now remember, we're looking at from the motor point of view. So that will include the moment of inertia of the motor itself plus the moment of inertia of the load, but transfer from the gearbox back to the motor. And we need to add these two together and make sure this number is small enough, not over the limit. So J motor is given by table 2, which is in the next slide. And J load, this is a moment of inertia that from the payload. There's a simple estimation we can do, and it's quite hard to actually calculate it exactly. In MECH215, in the later, when you calculate the static and dynamic limitations, you will see a lot of time the moment of inertia, this J, is quite hard to calculate when the shape is not kind of regular, like circular or rectangular shape. If it's just random shape, calculate this is quite difficult. Use pen and paper. Then J load motor is the moment of inertia of the motor that kind of mapped or mirrored to the motor, because there's a gearbox in between. So this moment of inertia will be kind of smaller, seen by the motor. And this is the table 2, shows the moment of inertia of typical induction motors. So other kind of different motors from different supplier will have slightly different number, but in the ballpark they are similar in this range. And in most situations, this moment of inertia from the motor will be quite small compared to the inertia from the load. So this is a small portion of that limit. So you can see with different power rating, when the power rating increase, the moment of inertia increase. That's obvious because the motor is getting bigger. And also with the RPM differently, even the same power, the motor inertia will decrease with the speed. That's also understandable because higher speed, same power means lower torque, which is a smaller motor. But how do we find the rotational inertia of the load? Some of the products like gear reducer and pumps, the manufacturer provide some standard data for the inertia of that particular machine. If the rotational inertia is not given by the manufacturer, for example, if you're going to design a gearbox, then this J needs to be calculated by yourself. We use a equation that to approximate that J. This formula shows how to calculate the rotational inertia J at the load side, which is simplified as half of the mass, the total mass of the gear, multiplied with half of the gear PCD square. It's basically the radius square here. This PCD is the pitch circle diameter, which we assuming the whole mass of the gear is kind of consolidated at its pitch engagement location. And for the shaft, we can pretty much ignore its moment of inertia because its mass is kind of concentrated at the center of the rotation. For the inertia, it's the mass multiplied with the distance of the mass to the center. So it needs to be further away from the rotational center to make the inertia big. So we only need to calculate the inertia for the gears, not the shaft. And remember, this J load is the inertia on the load side. When we calculate the motor, we have to convert this to the motor side. So we have to calculate the J load over motor. And this number needs to be divided by mv square, which is the gear ratio square. So the actual J on the motor side is much smaller than actual J load. And this is also a reason why we use a gearbox. With the moment of inertia, if we wanted to calculate how long it takes to acceleration, we need to calculate the torque first. So torque has three components. The first component is Tm. We have this symbol as a Tmav over m, which is namely the average motor torque from the motor side. So that's the motor torque from the generated from the motor. The second symbol is TL over m. So this is the torque from the load and reflect back to the motor side. So it's not actually the torque on the load. It has to be divided by the gear ratio square to get this load. Then the difference between these two is called a TJ, which we call the dynamic torque. This is the torque available for the system to accelerate from start to the rated speed. So we can see this is the formula we got before. So the torque equal to J, inertia, multiplied with acceleration. So if we know the torque, we know the J, then we know how much acceleration we can have. So alpha, this is d omega dt, equal to T J over J. So now we know how much acceleration we can have. And then based on that, if we have a certain rated speed omega, then use omega to divide by this alpha, then we know how long it will take for the system to run up. So accordingly, figure 4 and the table 4 and table 5 are as following. Table 4 give us kind of the average load torque for different type of loads. You can see there's a jaw crusher, and there's an impactor, there's a fan, there's a different kind of type of loads. And at different speed, you can see its kind of torque changes accordingly. Sometimes higher, sometimes lower. It's not exactly constant. And on the last column, that's the average. And for the calculation, we normally just take this average, the torque, as our kind of load torque to calculate this acceleration. The last column, these numbers 60.5, 38.5, is the percentage of the load during the acceleration compared to the normal working condition. Figure 5 shows the motor torque when it starts from 0 speed to the full speed, how the motor torque changes. You can also use the last column, that's the average motor torque as a percentage of the rated motor torque to do the calculation when during the acceleration. This information can also be read from the figure 7 on page 9 in this slide. Now with the T and J, we actually can calculate acceleration alpha here. For the acceleration time, we normally start from omega 0 equal to 0 and get to omega, which is the RPM of the normal rounding. And we change its form. It can be also shown as T equal to omega over A. So T is called run up time, or sometimes we call it starting time. If we use omega in RPM, so the conversion between radians per second to RPM is multiplied by 2 pi and divided by 60. So this is actually some motor manufacturer will limit how long this T can be for starting. If the run-up time is longer than this T, the motor will be overheated. So this number typically is 10-20 seconds, not allowed to be kind of running too long. So there will be other operational requirements which I will cover in next part. And up to now, we basically look at two kind of calculations. One is we calculate the normal running condition, what's the speed, torque, and RPM for the motor. And the second is how do we find out the limitation during the startup. In real applications, the operational environment factor is also very, very important. There's a lot of information. If you open any motor catalog, there's a lot of information about how the fertilization is designed, what is the protection rate, and what is cooling setting up, and how the motor is mounted. Can be foot mounted, can be flange mounted, and these information are on the catalog, and we will going to cover a little bit in the next part. To summarize, these are like 15 steps if we don't have anything we need to do to design a motor for the system. So step 1 is at the load, we have to calculate what is the load and RPM required for the application. So for your project, these are given. Step 2, have to identify how many different gear sets depend on the kind of gear ratio. Do you want a single set or double kind of set of gears? So in your case, it's only single gear reducer, so that's also given. Step 3 is the loss of the each gear set. Normally we assuming it's like 3%, but it's depending on different type of gears and depends on your design. It will be slightly different. So these three, pretty much from your project point of view, it's all given. Then the step 4 is the minimum power the motor required. This is normally you know the load power, then you just divide that by the efficiency. So that's the motor power. And then you check what kind of power supply available do you have. Do you have 3-phase? Do you have only one single phase, or do you have DC power supply? Based on that, you select your motor. So step 4, 5, 6 is also kind of given, straightforward. Then step 7 is to choose minimum motor speed and full load power. That needs to start actual serious calculation. Then you calculate the speed the normal velocity ratio, the gear ratio. Then you adjust the reducer ratio based on the actual motor speed, because the motor speed only kind of available in certain kind of values. You can't have continual options. If your calculation shows up the required speed of motor is slightly faster or slower, you have to adjust the toolbox, the gearbox accordingly after that. Then next step is to check up the run-up time or starting time, or you check the total rotational inertia. You just only need to do one of these two to make sure the motor actually can start. Then step 11 is checking the mounting and the shaft requirement for the motor to make sure that motor is able to fix it somewhere and be able to connect to the gearbox. 12, checking the space, make sure the size of the motor actually can fit in the given space. 13, check the environment and operational conditions, dust protection, and so on. Then 14 is just confirm your selection or modify your selection if some of the requirement in the previous step doesn't satisfy. Then go to 15. For some cases, if the motor speed is not kind of fixed, you want to have your payload changing different speed, then you have to be able to adjust the motor speed. And the way to do that is to design or provide a motor variable speed drive. So you have to select a suitable VSD for the purpose of your motor. Before we start, I'll give you one example. This is the example I'm going to work through during the lecture time. So at a power plant, a motor-driven bucket elevator is required to raise 1 ton of coal to a height of 18 meters in 1 minute. So that kind of gives you how much power the motor needs. And the elevator is driven by an electric motor via a worm reducer and a chain drive to the elevator head shaft. So you get like 2 steps of gear. So the worm type of gear is have a gear ratio 48/1. The chain drive, you have the output sprocket is 191. The head shaft sprocket is 573. So it's kind of 1/3 ratio with a chain drive. And we know the PCD speed is 0.3 meter per second at the output. So that also corresponds with the speed of the elevator. Also, we are given the moment of inertia for the load is 7.24 kilogram meters, and the efficiency of the drive is 70%. And based on that, we have to do the following and choose one of these 4 motors that suits the application. So given, say, this is the catalog you're having, you have to choose one motor out of these 4 to see which one is actually suitable for the task. So keeping in your mind and trying to ask the following question step by step. If you can answer all these questions, then you pretty much finish the design.